Hello, welcome. It's some months later, or rather August 30th, 2023. And it was a couple months ago when last we left off with about episode 44, 45 of Descriptive Differential Dynamics, with the idea being trying to help elaborate on the theory of differential equations, which are all things that study change over time, and feedback and the linear and the nonlinear, what with respect to mathematical models make for dynamical models that are explaining things that are as simple as line drawing and a velocity in the linear, and on things as complicated as impulse response, or that which is cyclical, or that which has many inputs, and these kinds of things, the nonlinear, and that there are many courses of the approaches of the methods and the formalisms that this elaboration got in the idea to help define dynamics, these descriptive differential dynamics, as about basically this notion of symmetries, sheaves, and submersions, with those being basically three kinds of approaches to help reach the sensible and then the fungible and then the tractable of these systems, to help arrive at a way that a person with this sort of second course in dynamics can arrive at having a reasonably thorough a vocabulary and the technical knowledge needed, or it's for my own sake, as far as that goes, as a way to address the field kind of generally and as a whole, that there's these symmetries and submersions of fields and sheaves to help express that for algebra's sake and symmetries, and then for these numerical methods' sakes and the submersions, or that which can be solved in closed forms if not being generally applicable, that the algebra and the methods of symmetries kind of expand the methods of available, and then the submersions kind of reduce the methods available, but for given ones might work and have closed forms. And then the sheaves is basically for all matters of topology, the usual open topology of mathematics, which is the description of a neighborhood of points, and which ones the properties define whether a point and all the limit points near it and the critical points next to it indicate whether it's dense, and as to regards domains that are continuous domains, whether they're continuous. These are the kinds of things that go into then after the notion of differential equations. First, the fundamental theorems of calculus, the integral calculus, and the differential calculus. And then the notions of things like the exponential function, which is its own antiderivative. And then here the sweep function, which is its own antiderivative. These being basically usually the only known function that is on antiderivative, and then sweep being a special sort of function deep from the heart of the foundations of mathematics and the continuum, as the line drawing and the spiral space filling curve. That adds up to having the same properties, and making for that the exponential function then is the distinct type of thing instead of a unique type of thing. That there are discussed here similar other examples and methods as regards to like the complete ordered field and the line continuity and signal continuity. These being particular harps of mine, or things that I harp upon, and not necessarily so that with regards to mathematics sometimes they're phrased as Jordan measure, or the complete metrizing ultrafilter, or the Dirichlet problem, or some of these other things that don't necessarily so reflect how they're central and primary, and that they add up as from the bottom much more than kind of adding up on the top, and that without resolving why they'd otherwise be contradictory in the topologies, in the sheaves, as it were, bringing in the sheaves, that without that then there's sort of the conscientious mathematician's mathematical conscience is panged or stricken by the fact that without such ponts or bridges and attachments that come together, it would be hypocritical. So that said, what I left off was just kind of reaching an algebra and the deconstructive accounts of algebra, and coming on down from arithmetic and this kinds of things, and getting into equalities and inequalities, one of these things is not like the other. And about how the notions there's tautologies and identities and equalities, and there's a way to look at those as all exactly the same thing, extensionally down through the middle, intentionally down through the middle. That intentionality is absolute equality, and extensionality is, for the purposes of logic and relations, not different and equal. Identities and qualities and tautology is basically defining those relations that we call equals. And then there's inequalities, whether these inequalities either reflect different, not same, or near and far, and close and distant, and reflect orderings. That orderings are so inherent in all things mathematical because it reflects all sorts of quantitative relation in systems of units, usually, that we ascribe to mental models, of mathematical models, of physical models of things that are real, and for that matter, anything you might consider in terms of its color, shape, form, proportion, or anything else that's qualitative and quantitative. So that said, now I've just figured to kind of rewind a bit, because I haven't really addressed any of these things much since then, of the descriptive differential dynamics. But what I've been thinking about over time, when I take a few minutes every day and think about, well, how am I going to pick up this thread of the descriptive differential dynamics and make for it so that it has some continuity, or what's the greatest thing I've found so far that I want to continue to try and elaborate and enunciate. And what that is this notion of the stop derivative. So what's the stop derivative? Well, the idea is that when you talk about motion, classical motion, you might have heard of and be, of course, absolutely familiar with these two notions of motion of Isaac Newton. That which is in motion stays in motion, and that which is at rest stays at rest. So this is basically the idea of an inertia and momentum kind of put together with velocity, and we learn about it in usual courses in physics, in terms of position and displacement and velocity, and of course all in terms of time. Everything here is parameterized by time. That then the notions of the inertia and the momentum, and what's at rest stays at rest, and what's in motion stays at the same amount of motion. Okay. And that there's no inputs of work required for a body to stay at some kind of equilibrium. And then when something's moving, if there's nothing else in its environs to so change its motion, that is just its motion with respect to the rest of its environs. So there's kind of like rest and motion. So in physics, when they talk about that, they have kind of what's like the rest frame, or the frame is any inertial system, is what the word is for any sufficiently removed body from other bodies around it. Like the Earth around the sun, or a person, or an ant upon a board, or something along the lines of anything that's an own independent sort of body is a thing. Well, at the same time, the ant on the board together is an inertial system. The person on the Earth is an inertial system. Earth and the sun together are an inertial system. So frames are everywhere, just like the origin is everywhere. There's a frame centered on anything. And so then that frame is basically, its contents are the kinetic contents of what's in the frame in terms of massy things that have the property that they have mass. And so the notion that objects in motion stay in motion and objects in rest stays at rest, of course, also refers generally to the massy objects. Those things which in gravity have weight, and according to how many atoms they have, by how many Avogadro's constants, many moles of atomic elements they have, is the mass. And so then the idea with the frames is that when there's any kind of displacement of an object in terms of its relative motion to other inertial systems, it's described as in what frames they're in. All right. So you have relative and absolute motion, and then relativity with frames, and then there's no privileged frame. Every frame is its own unique kind of space. And at the same time, they all intersect. And they're also concentric. It's just a basic notion that really much is the same thing as like a point in space. and an origin. Just like anywhere else you'd say on the Cartesian, we have coordinates. And so according to any two coordinates that cross, that origin is where it's like so. So, what is the idea of the stop derivative? Well, the change of the displacement, or the change in position over time, or the dp dt, is velocity. And the change in velocity over time is acceleration. And the change of acceleration over time is another higher order derivative of that. So when it's a zero at rest, it comes down that the only like the first order higher than that is the velocity in this rest. So Newton's got like either 0 or 1. But acceleration and everything above that, all the higher order moments of acceleration, then snap, crackle, and pop. Those various are just called jerk. Like what's the jerk that causes the impulse when you think of it as like a linear thing and a unit time impulse thing? Those are the names for these higher order moments up after acceleration. And then correspondingly is downward from deceleration. And so the idea of this is that then for what is acceleration and how can you measure acceleration, and then what are the results when two things impact or when things begin to accelerate, and how they exchange the momentum is the thing in physics, how inertial systems have that things meet and part, that there's the kinetic, which is a linear, and then the kinematic, which is rotational, which makes up so for how these things are, and the general terms. All right. So what is the stop derivative? Well, the idea is that for these first order things, then as you take the derivative, then they just go down to constant and then to zero. The derivative of a constant is 0. Now, when you think of the negative powers are like n to the negative 1. What is the displacement, and how to make that a mathematical model is something I'm trying to figure out. A mathematical model, a physical model. Because the mathematical model is just like if you take the antiderivative of something to the negative power, then it just increases in rank towards 0 again. But as it and so when you take the antiderivative from a 0 and then 1 and dot dot dot, it just it increments the power of that variable. But when you get from the negative 1, and it doesn't go from negative 1 to 0, it goes from negative 1 to ln x. And then it has this x to the ln x minus 1. And then it goes up and until it gets to 0, it never quite really gets to 0. And so the idea is trying to figure out what the stop derivative is how it's seamless and goes from the higher orders down and then the lower orders back up. Because then the idea is to frame the whole notion of acceleration, the computation of things, in terms of the stopping distance. So you have the acceleration is the time it takes to accelerate to something. A stopping distance is the space it takes that accordingly as something is accelerating in time, that it reaches that same kind of complement, the complement. So it's about framing the problem, framing the setup and the ansatz in these mutual terms. Because the goal is to look for how to make a deconstructive account of this the stop derivative, so that it ends up that there's a way to describe those families of formulas that roll up from that to help describe acceleration and deceleration in these terms, that they relate back to each other. Just like as the one is going to infinity, basically, as it reaches to 0, it has these infinite many terms that go out, whereas what keeps things simple from above is that they come down to 0 and just fall to 0. But they're really two sides of the same kind of perspective and projection that go forward, which is why I found that when and came upon this is kind of an idee fixe, that once I started thinking about that and looking how those were symmetrical and complementary, yet different, so they somehow meet in the middle of nowhere, and these other terms that were brought on in the 40-some hours about differential dynamics that recorded a couple of months ago. The idea is to bring up with that as well this stop derivative. And so that I haven't really found anything about that more. I haven't really studied for it. I haven't really looked for it. I have been studying a bit of mathematics. I'm always studying something in mathematics, and so recently mostly I've been reading Kant and Descartes. And why? Well, because like I just the other day got some books on Galileo and Descartes, and been reading about Newton, like Eric Temple Bell's on Newton, and these kinds of things, and helping to relate that like Greek science and the notions of the antiquarians and Pappus and all that, which is kind of where we left off, and reading from Kazarinoff about geometric inequalities and the arithmetic and geometric means. That the idea of the Laplacian and this kind of stuff, which is kind of nexus what follows from that, is to make and figure out what these continuity laws are, so that then when we figure out when something gets pushed and it tips over, then and then how that was kind of started rotating, or any kind of impulse and response that we normally think of two perfectly elastic billiard balls colliding and bouncing off each other, conserving their momentum. Vis-a-vis something, every time you take a step, lunge, that it works out that that's more of a rest exchange momentum. The momentum is in a system of these inertial systems, a rest exchange. And so you might say, well, why do you care about this rest exchange momentum? What's that supposed to be? Well, it's a way to look at conservation of momentum, which is one of these invariants in physics. And all our continuity laws, or laws of symmetry, conservation laws, are based up about it. And the idea is that it can be that the rest exchange momentum is rest exchange. It's the exchange of rest, of these rest frames, so that at the same time something, it's if it's not necessarily continuously accelerating, but it is leaps over bounds accelerating, that it gains overall momentum, even though if you were to add up those pieces, it would be positive, negative, and positive and negative. This was the Loch Ness monster, about what which is a serpent or a snake, and it's got waves above. It's got a wave above the surface and a wave beneath, and they exchange, and it's able to gain traction and go. This rest exchange momentum. And Nessie's hump, which is an expressing of this lunge, or leaps and bounds, or these ideas about how what can gain momentum, even to be able to describe something like a sling, or a discus thrower or something like that, as they spin around, how to describe the translation from the rotational to linear. Now, I was kind of inspired about this because when I was reading from Einstein in his Out of My Later Years, he goes into a big deal about Newton and classical motion, because he leaves down for relativity that these inertial systems and in the space-time, that this is where then I kind of attach this rest exchange momentum theory and light speed rest frame theory for special relativity, that it goes with what's called Fitzgerald contraction, which makes space contraction. So that when an object moves linearly according to kinematic, it actually brings the wave of space along with it. It transports space through space. And that then this ends up being the same kind of idea and approach for classical systems, with the idea being to help write what are formulas for the angular and linear together. Now, this is what I'm just kind of coming up with now, is the notion that there could be a way to write the rotational and linear attachment and the exchange of this in a similar sorts of way, to help explain why then that something like the stop derivative might be a useful framework or a setting to write some of these values in quantities, so it results that then they can be so sensible, fungible, and tractable, but in a deliberate sort of manner elaborates on what and why these quantities can be so written like so, and to help make up for the mathematics, all this constant give and take, which otherwise is like the variadic or the adiabatic or the perturbative or the hypothesis of perturbations or the virial theorems, and these other kinds of approaches that help explain for like Brownian motion or that which vacillates and oscillates still shakes its way through, as like the flagellum. How does the flagellum of the bacteria that it is this tail that it shakes to send itself along work, compared to how do feet work to propel you in swimming, or that kind of thing, which is it's got a pretty simple definition and explanation, but is here for helping explain that besides the information that goes into it and the fact that there's various surfaces, you can adjust their configuration and make the kinematic and so on to then apply force with advantage and gain motion, and that nobody can spin around in a chair, although you can kind of hump it around, but it involves there's no real gain there. It's just making use of these things that from Newton's laws and Einstein's laws and the laws of physics that we have. Then the idea is to help figure out some ways to write or what the usual equations of motion, so that then they can make up for, after an analysis, what's sort of follow. And this is kind of what I'm looking at, this approach that might be possible to get over this pass. I'm not quite sure if I'm brave enough to try that or have the guts or the time or the brains. But then that's the idea of this concept, at least. So then it's conceptually, bringing that back down the mountain, that then somebody will say, well, I see you've worked up these equations as they make the antiderivatives of negative powers. And on their way to zero, which is then where they'll go, is that you developed something that will describe what would be a growing or vanishing quantity in particular related terms as it goes around, to make it so then what's in this one variable, it's univariable, that the stop derivative still makes it so that it adds up and it builds up in a system of complements for the operator calculus, that according to my gesticulations and these explications, that it will help to provide a fixture. So where I arrived at that, just in recapping, or it's been a while since I talked about it, but was first I started looking at differential equations from these university mathematical texts, these being, a grab bag assortment of a year or two or more of mathematical textbooks that, fit in a lunch bag. A small lunch bag. And what's in them is all the sorts of these things from when the course of differential dynamics was still more for the integral equations and their plane curves than the differential equations and their solutions. So the plane curves are the solutions to the integral equations, and similarly the differential equations and their solutions are the integral equations. So there's entirely two different approaches about how to frame the whole thing. And so when we find this course today, what you get is differential equations and their solutions, because then after stuff like Sturm-Liouville and the existence and uniqueness of solutions and initial value problems and boundary value problems, then there are lots of numerical methods which become available and that are very well understood and well known, and make for approaches to getting solutions out. Compared to that, then this older approach and the system, this theory of differential equations was in development since antiquity. Anything like the brachistochrone and the tautochrone and lots of different things are differential equations. It's all dynamical modeling, then with regards to the inventors of the calculus, the discoverers of various methods of the integral calculus, or Newton, Leibniz, and their priority dispute or whatever, but Newton and Leibniz, and then getting into the Bernoullis, and then Maclaurin and all that, and then Taylor, Maclaurin and Taylor, and then they get into a lot of these systems out Fourier, and then that's when they start defining these first, second, and higher order ordinary differential equations that, of course, map directly to physical things that have to do with the square, inverse square, all these kinds of things. And that were defined in parameters times in terms of time and also in terms of themselves. So any kind of function you can say is in terms of time is kind of differential. But and it's about the differential is the name of the infinitesimal analysis. But then these ones that are defined basically in terms of the exponent is where they find a lot of their solutions. It's got a lot going on. So up to that kind of framework, and then the ordinary, and then there's some also very simple and usual and regular systems of equations that are not ordinary and or linear, and they have multiple variables, and then there's various notions when they're separable, and then it can be treated in terms of treating each other constant, and then also what it means in the reformulation when they have interacting constants, interacting qualities, running constants together, that these are things going on. And then trying to figure out from that, the study of these books, and kind of refresh myself from having a mathematics degree. I mean, it helped me understand these things that I set through years of courses, and I was pretty good at it. Then reading this course, I started to develop some ideas that I thought might help me address how to understand these things. So after the first idea of getting into descriptive differential dynamics and breaking down the field and helping to disambiguate the definitions, because by then you'd find somebody who say a function was for their differential geometry of a particularly more limited class, but then it made things more tractable. Or when you have something like the introduction of the algebras and this kind of stuff that goes into it, I wanted to make sure that those kinds of things are disambiguated up front in such manner as that then it would be possible to address the literature and the field kind of thoroughly and comprehensively, and without winding up 10 miles down the road having gotten the wrong kind of gas or something like that with regards to the definitions and derivations and derivatives make this unbroken chain of what's really for the formalist critical to not be a hypocrite, to not be hypocritical, to not be wrong or unjustified. So, and then this is just recapping again to where I can catch up and hopefully trying to figure out a trail to this stopping derivative. Is the idee fixe that started to arrive was this identity dimension. And so what's the identity dimension? It's like, well, I'm very used to looking at the XY coordinates and thinking of things in terms of X and Y. If I think of an abstract plane with an origin, I imagine the 0 point, comma 0 is a point at the origin, and there's two axes, X and Y, and an axis is something about which something rotates. And as well, then it's usually implied that these are meters, and so really it's not necessarily the word for what is the center of this coordinate setting, except insofar as it expresses exactly that these to make these rotations out of the plane and back into it really does make them axes, like the complex analysis maybe, or anything that's this multiplicity theory, as we've been talking about after singularity theory. What's singularity theory? It's multiplicity theory where you pick one and ignore the others. So for these kinds of things. And definitions, and using definitions deliberately, knowing where the food comes from, knowing where your food comes from, chewing the food, and knowing where the terms all arise from formally. So where does that go? The idea fixe was then, the for the usual way I look at a plane, well, I want to look specifically at one of these, just the x-axis. So I figure, well, instead, I'll think of the line that's x equals y that goes from the origin right between the two, and so it's called x equals y, or identity function, and f of x equals x, and I'll consider that to be the axis, and so that way, and then all of a sudden I have what otherwise I term in terms of x and y. I could write anything like that, and then however it shows up on this identity dimension is a function in that. So instead of having one variable then two variables, it's like having one variable with two variables that support it. And so this is a very general type of thing. Even when you're thinking about, like, how am I going to go from infinity down to the infinity and down orders of acceleration to zero and a constant, and reflect that kind of means from the infinity and up, and then when it reaches zero, then it goes out and out, the stop derivative and how those come together, then it's not too dissimilar in metaphor from trying to figure out that, well, I've just got one dimension, and I'm going to think of it in two dimensions, but they share an origin, and then that which tracks on one or the other would define for me that if it goes to infinity in the one, it kind of goes to infinity in the other, and in this kind of manner, then if it's drawn to draw these systems, how they can go and relate that in x and y they're related can be whether or not they meet on the identity dimension line, right? So these are only positive numbers so far because, well, if you include the second quadrant or the third or fourth quadrant, then for even functions it works out for the fourth quadrant, but not really otherwise, and it keeps things simple, and right now we only have positive numbers, we only have positive integers, and then we start getting into rationals and and that kind of thing. There's a deconstructive of arithmetic, deconstructive accounts of arithmetic and algebra, and for this function theory and topology are two big things here in operator calculus that then we make up for geometry and number theory, that those are the elementary objects that all live together in terms of this geometry and then this vector space and these kinds of things. So the idea was that the identity dimension was a pretty cool thing. And, well, how cool is it? Well, it's like dividing by zero, which is a bad idea. Why is that a bad idea? Well, because it's undefined. It's a multiplicity theory, and it's infinitary, meaning that there's no reason to divide something by zero because you won't get an answer back out of it. In the sense of an operation being closed in arithmetic, the complete ordered field is totally closed for addition, subtraction, division, and multiplication, except division by zero. At the same time, it's a thing. If you can imagine, it's like, whoa, we just actually took the whole space in that quadrant, we just shrunk it to a box in the upper right corner, we call it infinity. Point at infinity. The projective point at infinity. Various fields and approaches and formalisms for approaching large numbers and infinity in mathematics make for a notion that there's sometimes you can say that division by zero is a thing. Like when you say, well, I'm not really up to infinity, I only go up to 100. And then, so multiplying by 100 is kind of like division by zero. Like if I decimate something or divide it by 100, zero is what's left. And that's just a matter of what's effectively the inverse of the multiplicative annihilator. What's that? Well, the identity, multiplicative identity is 1. If you multiply something by 1, it's 1. And the additive identity is 0. If you add 0 to something, it's that number. So something times 1 is the number, and especially if it's 1. And something times 0 is the annihilator. And so the idea that there exists a reciprocal to the annihilator is the generator of sorts, or the roots of 0, say. Is this kind of notion. So, like dividing by 0, this identity dimension, when you get into these notions of the first things that the course in the university text gets into in the differential equations, and it's in the integral equations, is this linear fractional equation, and so the actual x equals y line drops out. Right in the middle. And similarly, in Clairaut's and D'Alembert's equation, and this was kind of read off briefly, I mean, I just kind of talked through it as I was looking at this. It's right in the middle. It's kind of like division by zero, but for completion and non-standard things, it's part of the envelope. The envelope that these orbits and orbifolds have their trajectories and their manifolds. Generously, thank you. And that the envelope is like right at the skin where it still admits a solution, in fact, multiplicities, multiple solutions. And then that ends up being where there's perhaps the most room for the tractability in the things, because it would help arrive at the what's otherwise not even fungible. To make something sensible first, and then fungible and tractable, is for these cases in the non-standard, like infinity and infinitesimals, that it needs to be established first deductively they even exist. So in our linear standard curriculum, they don't. We build things up from delta epsilonics without having to rely on that, which is really important because people do not have that many fingers. But at the same time, there are some aspects and features of it that it directly and only eventually, and for finally some ultimately only, become available from the deductive analysis. The old notion that something that has constant motion, you can divide its time into half and half and half and half and half again, that is stopping halves and halves and halves and halves and halves again. But it still reaches the limit and say, oh, the limit that's its limit, so it's no different. But from the other side, when it's also coming from their side, it's like, well, that's no different either, but they're always different. So to actually meet in the middle is that the limit is the sum, providing deductive grounds to believe, to have a factual sort of proof that it's necessary for the rest of the things. So that said, then this notion of the identity dimension was brought in to help then write about how you could have this complex numbers. And again, I'm just kind of recalling some of these toys, these as setups, these systems, these ansatz, these objects of mathematics that were built and kind of defined as I'm trying to understand and describe their properties, because I'm figured to use them as kind of like a bench setting that then will make it possible for me to deconstruct a lot of these other things and to write a bit of my own sort of mathematics as well. And it's not that I want to do things my own way. It's that I want to do things right down the middle, straight from the heart of things, because I study foundations. And so this is kind of just what strikes me as what might be a reasonable way to make a deconstructive account, like the addition and division we were talking about, and these other ways to look at mathematics in kind of fresh ways that would that so far I've developed them as what I call the idee fixe, which is French for, it means fixed idea, and it usually means a sort of psychosis, or a mania of the idea fixed is like something that's unshakable otherwise by observation. It's just something that's generally that regardless of what else happens or what else is presented, it will not be disturbed or moved or changed. So it's the invincible ignorance of a sort. But as an idea fixed, really it's just a term that when it comes to that, according to all the other terms that have been introduced, for example, in the course of a linear instruction or in a setting or something like that, it would not exist. Well, I just keep a place that exists. It has a home there in its mental world, and so that is an idea fixe. And so I think that Platonism and the University of Mathematics, and the objects in it is an idea fixe, strong mathematical Platonism, which I find really very compelling and really comforting. It's always there, but it's not necessarily. It doesn't necessarily do what you want. I mean, you have to know the right phrase. You have to know what you're looking at, to get the results out of it. But it's there. It's all right. So, anyways, then there was this identity dimension, and then this complex frame. Because then using the other quadrants, it's possible to consider the octants as like a half plane, because then there's a way to write stuff and see how that would be a matter of projection and perspective. Well, what does that mean? Is like, well, I only have eyes in the front of my head, and so when I think of everything, it's basically out through the light cone, kind of like who's that? Hawking and the light cone, and that's this entire future state is what's in front of it. In terms of then that otherwise the origin is everywhere, and the origin is the center in the middle of things, and all the different directions, forward, back, left, right, up, down, with respect to 3 dimensions, are with respect to an origin and an orientation. So it just kind of reflects then that in the course of a ray, usually that being a vector with a see, usually the head of the arrow is a sharp point, and the tail of the arrow is a flat point. So usually when you think of a vector, it's like I'm pointing to this point in space, and so the ray goes outward. When you have where it goes, that's where the arrow is, where you draw that. So a ray from the origin, or just a ray, that it's but that it doesn't really have, the ray is infinite. So I'm just trying to figure out whether to call the head or the tip or the tail that part of the ray, but we'll just leave it as the origin and the identity dimension, because it's only direction. And so if it comes to any point that you want to figure out how to attach negative numbers with it, it involves going somewhere out there in the middle and then saying, okay, now I'm going to treat that and go either way to do the work on either side of that to help build up what looks like a square and then a triangle, symmetrical. I don't know. So anyways, let's see what I have. I got Feynman, and so I'll take a look at him for a minute. So Richard P. Feynman is a quantum physicist, and what's he most famous for? Making continuum mechanics with some very simple things, with some very clear, simple things. He helps make some formulas and like the what's the word? Derivations and closed forms for lots of different things, and write things like the Brockhet notation and phi 1-2 interference experiments that I'm going to start looking for them, because I have this collection of this lectures on physics, and it's a 3-volume set that comes from Feynman, Leighton, and Sands. And what it is it's for physicists, it's for anybody but who studies physics. But it's got all these different chapters like quantum behavior, the relation of wave and particle viewpoints. See, viewpoints is very general, very general. Identical particles. This is I'm just trying to remember. There's a particular person who says that the Pauli principle from physics of the Wolfgang Pauli's particles are unique, but just saying the dependence of amplitudes on position. See, now that might be relevant, because the idea of this stop derivative is that it's to relate the kinematics and the kinetics, and then that with regards to the amplitudes of waves, that there's this oscillative and recitative that makes this attenuative and dissipative. And so these are these usual general principles that get arrived at, that, well, when an object stays in motion until it either attenuates and dissipates and comes to rest, or it oscillates and restitutes and changes direction and it changes back and forth. So these are the changes vis-a-vis the states kind of thing. Operators are key things. See, for this whole operator calculus, when you write something up in that, then you can use indexicality and just the order of things, the plain ordering and the numbers of things. They become quantitative, and then they have addition formula. like all the useful things that come from addition formula. Like the other day I was trying to figure something out. I was like, well, what is the factorial? Like if you multiply all the numbers less than it and the number, it's the factorial. It's called a gamma function for non-integers. So if you take the sum of a number from 1 to n, and you take that to the nth power, and then you subtract the sum from 1 to n of, from I equals 1 to n of I to the I, say, or so you take the sum to the power, and then you take the sum of the powers of the number to its own order, so less than this number. So you take the difference of those and take the square root. It equals the factorial. It's an identity, or it's this function. It's an approximation. It's off by a couple digits, but the larger it gets, the closer it gets. So it's an approximation with a vanishing error term. I discovered that some years ago, and I'm still quite boggled about it, because I was studying this other formula, and the reason I was studying it was because I derived it the formula from probability. And how it would arrive at was, well, I considered the space of all the zeros and ones, all the sequences of zeros and ones. But instead of looking at it as from starting at 0, the first and the second, and kind of running out the law of probability that way, I looked at all the rows and columns and made deductions about what would be in it. So it's called Cantor space, all the infinite sequences of zeros and ones in any order you like. But instead, it's like they're all in order, and it's square in a certain sense. So I built up this framework of the Cantor space this way, it's square Cantor space. So I made some deductive arrangements to arrive at what would be the the properties and the propensities, the densities and propensities of items in this space, and establish that it has the mathematical properties of being a space and that there are vectors in it and these kinds of things. So then I wrote a formula that's basically from classical probability, and plugged in some of these values, and because I was given that the property of this formula is that it's like so, but it happens to be built up from these numbers. And then I put that in, and of course for the small numbers it's wrong and it gets worse. The only way I could justify it was to make it so that it was from this thing. So this is an example of an idea fixe, because I had an idea fixe on this side and an idea fixe on this side. They didn't agree, so I got to figure out how they meet in the middle of nowhere, about the rule of various large numbers and laws of large numbers over time into infinity. So I started looking into writing relations for this expression, which could only be true in the limit. It's only true in the continuum limit, or for infinity. And then, as with regards to true, I started breaking it down and using some formulas I found from Abramovitz and Stegen and the table of series and integrals and products. And then I applied some novel mathematical methods about the reformulation, meaning to parameterize an object by its own thing. And this would be the same thing that would go on something like the stop derivative. What is this parameter that goes along when you have like a function that's logarithmic or exponential? Well, if you have another function that's linear and you want them to still line up the same, you need to multiply this by this growing constant that goes in. So you have one or the other in terms of linearizing the one by like transforming its coordinates or what, making it so that it's linear. That sometimes that's very simple and clear how it's done, but other times you need to put in the parameterizations that go into it that way. And it's not also a dissimilar approach from what we read from Mogan and the nonlinear electromechanical effects and applications. That's a way to establish what makes for a linear form, and this addition formula and the indexicality, and being able to lower the order of some of these higher order terms to make it possible for them to then be treated arithmetically and linearly. Okay. So with these and some approaches and figuring out some functions provided from Abramovitz and Stegen, or the Handbook of Mathematical Functions, special functions, and putting this formula into trying to understand things like the Stirling cycle and subset numbers in this. It's called the factorial exponential identity, because it basically reflects a relation between the factorial and exponential that I'd never seen before. It's like an identity or a formula for this. And it's not true for small numbers, as you can show that it's not true by number and number, and even as a case for induction, it's not true. But that is true for the infinity. So out of these developments, I was working on just transform the equations, which is usually a matter of algebra and keeping track of variables and keeping track of any quantities and the derivations and their terms and the conventions that goes into this algebraically. Out drops this equation that says n factorial equals the square root of sum from n to the n minus sum n to the n. And I said, well, that's kind of neat, because it just gives an equation for this in terms of that. The factorial, the product of all that in terms of the root, that's what really surprised me. The square root, how did that get in there? Because it's like the n factorial squared was this difference. And so you can rearrange terms, and it's just surprising to have these things related together. It's like an addition formula, but it's like a root negation formula under this power terms that reflects a factorial. So I thought that was pretty surprising. So I plugged in some numbers, and then the bigger the numbers I plugged in, the closer it got, the less different in terms it got. So then when I started thinking about, when I read something like Magin's, some of the approaches in the surface acoustic wave convolver, which makes it possible to figure out what to dial in to eliminate the nonlinear effects, or to make it keep things linear, which would otherwise reach be dominated by the nonlinear terms. That's an expression that comes out of these other ones. Similarly, with the idea whether the stop derivative would be interpreted or implemented, is it would come up, and as the terms got into this various things that kind of fall into and apart in terms of eventually by leaps and bounds coming to a halt, hop, skip, and a jump type stuff, would arrive in these differential functions, this kind of self-parameterization, this reformulation, this parameterization in the terms. And so then I applied a similar approach when I found it, because I'd noticed that I could keep the terms in line if I just took the one or the other and say, hey, this term will just have this adjustment continuously compounding, as it were, and bringing itself along, and arrived at basically a contradiction between, like, how many of the zeros and ones, how many sequences 0 ones are all zeros and all ones are all ones, all or none. They meet in the middle of nowhere, the square Cantor space, which is a thing. And it's one of the only kind of developments I know that is not available via laws of small numbers, illustrates multiple laws of large numbers, and is that kind of thing. So I've enjoyed that. So anyways, let's see here. So the other sections, we got semiconductors, which they have a breakdown voltage, and so what that means is, like, kind of like a capacitor is, that a semiconductor it'll wait till something rises a certain level, and then it'll, like, trigger and go. Semiconductors. But then there's also in the notion of semiconductors like the light emitting diode, and I'm confusing a bit the capacitance and the action and the function of the semiconductor. They're not so different, but they're kind of one or the other. But propagation, let's see, the hyperfine splitting in hydrogen. So I think with regards to the spectrum lines and these kinds of things. Angular momentum, symmetry, and conservation laws. See, that's where the stop derivative, and yeah, as I've set aside for a while and just not made any of these recordings, I just kind of put it down for a while. Then this, the idea that kept coming back to me is what I thought would be the most significant would be the stop derivative, because it would be a means to establish for something like classical motion and linear motion and the kinetic and the kinematic, what would be a contribution for the inertial systems, which would make for something like what I call Newton's zero-eth laws of motion. which are more fundamental, yet underneath the classical and unstated, the classical assumptions naturally arise from them. It's part of this deconstructive account of that. So that would be, I think, the big gainer for physics to have something like that. So angular momentum and some of these other topics and subjects that Feynman addresses are pretty relevant. The disintegration of the angstrom of the gamma degree. Let's see what that says. I haven't heard that. There's the typo. I think the disintegration. I heard of disintegration, but not disintegration. Let's see what Feynman, Leighton, and Sand say about this. 17.5 in volume 3 of this work. Okay. So, and it's right after symmetry and conservation. And it's right before symmetry and conservation. It's chapter 17, but I thought this is 17.5. Where did this go, Feynman? Oh, it's after that. 17.5. It's on page 17.11. Section 17.5, page 17.11. The disintegration of the... Here it's spelled disintegration. The disintegration of the lambda degree. Now I want to give an example of how I use the theorem of conservation of angular momentum in a specifically quantum physical problem. So, angular momentum is given as quantum numbers. It's like, what's spin in the quantum numbers? It's not really. It's like it's a qualitative constant, but it respects things with regards to phase transitions, and so it's kind of like spin, except it's not classical. It's not like the spin and angular momentum of a spinning disk or top, except insofar as it reflects this on this quantum level as part of a system of what's just a disturbance in the continuum force or the wave. To be a little loose on that, but it's a little loose, the definition of angular momentum of the quantum particles and angular momentum of the mesoscale, the middle scale, classical. We look at the breakup of the lambda particle, lambda naught, which disintegrates into a proton and a pi minus meson by a weak interaction, which are usually the output of high energy and high intensity collider experiments. Lambda naught goes to p plus pi minus into a proton and this thing. So it's a meson, and it breaks up into a proton and a pi meson. Assume we know that the pion has spin 0, so they call the pi minus meson a pion. That the proton has spin 1/2, and that the lambda 0 has spin 1/2. So the idea is that the spin is a conserved quantity, and then it's like in halves or 3/2 and this kind of stuff. Like the numbers and the quantum numbers are integers or halves. And so according to these various symmetries and parities, according to the system, that they can add up, and in the quantum numbers, in the field occupation formalism of the field theory and the quantum field theory, those are the terms, and why it's a little bit different than as these quantum numbers and the amplitudes and such than the classical quantities, which are more analog than these discrete quantum things. That's the whole great thing about quantum physics. After electron physics and Rayleigh and Dalton and all that kind of stuff, the ultraviolet catastrophe, and everything would add up to infinity. Well, no, we're just going to define the quantity of an electron charge and its mass We're going to say that's distinct. We're going to have a mole of atoms. We're going to be able to give that a number. We're going to have everything works out great according to the atomic chart, which is a beautiful thing. Everybody, that's one of my favorite things in the whole world is the atomic chart of elements. But then our models of mass, remember that the nuclear models and all this are models of what our surface is and what our interactions in molecules and the molecular physics and this kind of stuff. And so then that makes what our four the models of the nuclear models, like the Dalton and the billiard ball and these ones, and that when you think of like, well, what does it mean things are mostly the space and the atom? It's like, well, when you shoot the nuclei of gold and some of these other protons and things into the atom, how they reflect out about and around, or as if they spin off it, they catch in orbit briefly and spin off. That's basically modeled as if each of these atoms had a center. If you think of spallation and neutron bombardment and some of these other techniques that get involved. And why you say this, so compared to the two surfaces touch and they interfere, they reach each other and they don't like sink into each other or something like that. That's a different kind of thing. Then with regards to the mathematics of it, that there's like something's continuous and something could be discontinuous everywhere, or something could just be only drawn out, or these are this line, field, and signal continuity. Not so relevant here, but we do have a surface model. It all comes from electron physics. That's the mass and charge of the electron being the fundamental thing that defines things for the quantum. So all these quantum numbers add up real simple, and in the big formula end up they're contrived in either the diabatic or adiabatic or non-adiabatic to add up to this. That's why one of the reasons Feynman's famous, because he invented some means to keep these things simple. So then you can just you can keep adding them up and pile it on, and it keeps coming in, adds up. So. Soon we know that the pion has spin 0 and the proton has spin 1/2, and the lambda 0 has spin 1/2. Okay, we would like to solve the following problem. Suppose that a lambda 0 would be produced in a way that causes it to be completely polarized, by which we mean that its spin is, say, up with respect to some suitably chosen z-axis. The question is, with what probability will it disintegrate so that the proton goes off at an angle theta with respect to the z-axis? Right. In other words, what is the angular distribution of the disintegrations? So here this helps reflect that in particle physics, everything is a particle. But as a matter of continuum mechanics, and those being waves and particle-wave duality, it's really kind of just waves, wave displacements, and splashes, and coalescing back and forth. And so when Feynman's describing this thing that's kind of like a disintegration of particles, he as well has a complement of how to explain it in terms of waves. And the resonances, which are the greater waves, all this kind of stuff. So adding that back up and down, I'm going to leave that now because it kind of reached time. But the point is going to be that these are the kinds of things that we get into exactly as just consider, like what happens when something tips over, what happens in leaps and bounds, how does rest exchange momentum work, how does a sea snake hump the lake, and how is it possible to describe this in terms of classical motion, so that we can help give for Newton these, what Einstein was looking for, these inertial systems, bring back Newton's zero-eth laws. There's descriptive differential dynamics, makes what's a differential system, or the whole theory of the thing, in terms of the quantum mechanics, which is continuum mechanics, and all this kind of stuff that adds back up. Well, all right, then I'll try to figure out the stop derivative. And basically the notion is to frame it in terms of then experiments that could be implemented mechanically and terrestrially. Hey, have a great day. Or I hope you had a great summer. Good luck.